Hello and welcome. The following is the second in a series of lectures covering Chapter 44. Today we will be talking about nuclear mining energy and nuclear models. As we've seen with the carbon-12 atom, the mass of the nucleus is less than the mass of 6 protons and 6 neutrons. Seen in terms of rest energy, which is proportional to the mass, the total energy of the carbon nucleus is less than the total energy of the separate components. When a nucleus forms, energy is released, and therefore, to separate an atom into its components, you need to add energy. This is what's called the binding energy, and it's different for each element and each isotope. To calculate the binding energy, you just need to know the atomic mass of the nucleus, and then you just calculate, well, how much would the atomic number of protons plus neutron number of neutrons weights minus the atomic mass of the element in question, and times that by a conversion factor, since we like to use MeV in particle physics. You times that by that factor, that takes you from atomic mass units to MeV, and it'll tell you the binding energy, which again is basically how much energy you need to break an atom apart. So for carbon-12, you need to apply 92 mega electron volts of energy to break apart the nucleus, which comes to about 7.7 mega electron volts per proton or neutron in there. You can compare this to, the ionization energies, which you might recall for the hydrogen atom was just a few electron volts. So clearly, to get an electron out of an atom doesn't take as much energy as what it does to break a nucleus apart. Also note the formula. It might be apparent that this term accounts, for the total number of neutrons times the mass of a neutron. But for the term that accounts for how many protons you have, this term accounts for the mass of a hydrogen atom, which is just a proton anyways. So here is the table, or figure of the binding energy for the first 238 elements of the periodic table. So all of them have some positive binding energy, which makes sense. All of them, take some energy to break them apart. Note that the highest binding energy award goes to nickel with a binding energy of close to 9 mega electron volts per nucleon. And at this point, for heavier elements, the binding energy actually drops. It kind of almost becomes constant, somewhere around 8 mega electron volts per nucleon. The reason why that is due to the diminishing returns in binding energy, since as you keep getting this heavier nuclei with more neutrons and protons, the binding energy, which is basically caused by potential energy loss due to the nuclear force. Effectively, right, you get diminishing returns in the nuclear force, so it becomes a smaller contribution to the energy as the mass number increases. So eventually, the binding energy just kind of becomes fairly constant for elements with a mass number bigger than 100. And it's worth pointing out that if you look at the light elements, so the elementary ones like hydrogen, lithium, helium, carbon, so on, to produce helium, you need two hydrogen to fuse together. And because helium has a higher binding energy than hydrogen, that means the helium nucleus is more tightly bound than a hydrogen nucleus. Likewise, a carbon nucleus is more tightly bound than a helium nucleus. And no nucleus is more tightly bound than the ones found in the tan band here. But that means, though, that these elements have a higher binding energy than heavier elements. That means that for these elements to produce the heavier elements that follow them on the periodic table, they need extra energy. So hydrogen fusing into helium is an exothermic process. It doesn't need input energy. The hydrogens can just fuse together, produce helium, and also release energy. But for nickel and germanium, to form heavier elements like iridium or silver or gold or lead, that is an endothermic process. They need extra energy to form these nuclei, to form these elements, because those have less binding energy than they do. So that's why stars, have a cycle where they can produce hydrogen, nitrogen, helium, and so on over and over, because all these processes, hydrogen forming into helium, and then from helium and hydrogen, you get carbon, nitrogen, oxygen, and so on. Those are all those are all exothermic processes. They don't require extra energy. So the star just kind of fuels itself producing all these elements. But these heavier elements, do occur in nature, obviously. They're commonly occurring. But due to the fact that they're produced during endothermic processes means that the energy must have come from somewhere. So these elements were actually only produced during stellar explosions where there was enough energy for the lighter elements to fuse together and form these heavier ones, some of which are part of our own constitution. They're part of our biological makeup. So we contain elements that have been produced during stellar explosions. We are made of stardust, each and every one of us, each and everything. But why binding energy in the first place? It does seem that the neutrons and the protons, reach a potential well when they come close together, thanks to the nuclear force. But how do we model that? Since there's other effects to consider, such as the Coulomb repulsion. So how do we measure then how much energy um, a nucleus has by virtue of having all these interactions between its constituents? Well, research is still being done in understanding, how a nucleus behaves and what even it looks like. Well, we'll just talk about two models, sort of like an early one and kind of like a up and coming one that kind of mixes in the quantum mechanics from the previous chapters. We won't go into too much detail, but I just want to give you a picture of how we can describe the nucleus, by virtue of that, explain why the nuclear binding energy that has been observed for all these elements is what it is. So Niels Bohr had his own model for the nucleus, and this was a few years after he came up with a model for the hydrogen atom. But basically, in the same way that a drop of liquid has all these molecules, like a water drop has all these water molecules jiggling around. A nucleus is the same, where you have protons and neutrons jiggling around the core, the nucleus, in the same way that molecules jiggle around a drop. And they're just jiggling around, colliding with one another. And from the theory, he was able to derive this theoretical formula for the binding energy of any element with any number of neutrons. So this could account for any isotope of any element. And the formula looks like a mouthful. There's 4 terms, each one with a constant: C1, C2, C3, and C4. Everything else is a term either for the mass number or the neutron number or the atomic number SAD. So clearly the binding energy, does of course depend on how many neutrons and protons you have in the nucleus. So each term accounts for a different effect. The first one talks about the volume effect, which contributes to the binding energy, while the other 3 terms actually decrease it. As for the first term, which is well, literally first one, which is directly proportional to the number of neutrons and protons that you have. That accounts for the volume effect, which tells you that the more that protons and neutrons that are brought in to form the nucleus, the more binding energy you have. The second term, which has a negative sign, so it tends to decrease the binding energy, that is the surface effect, and that's kind of like a correction factor. It accounts for the fact that nucleons that kind of are stuck at the surface of the nucleus have less neighbors to interact with, so there's less nuclear force interactions happening, so that lowers their contribution to the binding energy. The third term accounts for electron repulsion, which makes you gain electric potential, so you lose some binding energy to that. And the fourth term accounts for the symmetry effect. Basically, Bohr noted that elements that have the same number of neutrons and protons tend to have the most binding energy, but when there's a big difference between the neutron number and the atomic number, the binding energy seems to decrease, so the term accounts for that. As for the constants, they were meant to be determined by fitting observed measurements of binding energy. So in the same way that you fit a line to data, or you fit a curve to points, after doing a lab, Bohr did the same thing. You just take binding energies that were found and fit his function for binding energy to the points that were found, and find the constants that work with the data. The formula did work well enough, at least for the measurements at the time. But there were some pathologies that the model, the liquid drop model, which the formula was derived from, it couldn't really explain. Also, the model did not account for the angular momentum of the particles, which was discovered to be an observable quantity of certain nuclei. So, very rudimentary model, but still a working model that in the future some ideas have actually been reincorporated into leading theories of the nucleus. Anyways, in this question, they're just showing you how you can, with the constants, with the fit parameters C1 through C4 that were derived using experimental data, you get asked to calculate the binding energy of xenon 64, and experimentally, it's been found to be about 559 megaelectronvolts. And using Bohr's theoretical formula, it's predicted by the energy of 560. So it's a pretty good estimate when you consider the time it was developed, when he did not have a full picture of the nucleus. As for a better model, there is the shell model. But before we get to that, we should probably explain why the liquid drop model didn't work that well. And that's because there's something about the nuclear structure that the liquid drop model didn't quite capture, which is the fact that atoms like to have an even number of neutrons as well as an even number of protons. It seems that when you look at the binding energies, there seems to be this magic number, which is values of n or z, where the binding energy is higher than neighbors of slightly different n or z values. So if you take Bohr's theoretical formula for the binding energies and you calculate that for all the elements and their isotopes and compare those theoretical results to what was observed, you get this graph. So these are the residuals of the observed binding energies minus the theoretical ones from the Bohr model. And there seems to be these magic numbers, which are all even numbers, where there's a peak in the residual. So here's a magic number, here's one, here's one. So it seems that when there's an even number for n, z, or both, the binding energy is more than what is predicted. That means that these nuclei are more stable than predicted. So The Bohr model, the liquid drop model, doesn't have an explanation as to why we have so much stability in these situations. And if you look at the data for ionization energy of different elements, you'll note that the noble gases seem to have the highest ionization energies in their groups. So, more than any of their neighbors, it takes more energy to remove an electron off a noble gas than any other element. In the quantum mechanics chapter that we did not talk about this, we would have seen that noble gases like helium, neon, and argon and krypton having, a certain number of electrons such that all their inner they're called electron shells, so they're kind of like this like spaces around the nuclei that can be filled by electrons. All these shells are evenly filled, so the state that all the electrons are in together in these noble gases is a very desirable state for atoms, and it's one where the momentum of the electrons basically balances each other out, it cancels out. So the configuration of electrons in noble gases is one that's very desirable, one that's like minimal energy. So they're very stable, they're very grounded, which means that it takes a lot more energy to get an electron excited enough that it jumps out of these noble gases. So perhaps the sort of motivation for developing a shell theory for the nucleus was that perhaps this was the same thing that was happening. The elements that had high binding energies had that because their nucleus was very stable. That the that the neutrons and the protons were occupying all these states that were very desirable and were like evenly filled, and perhaps even had their own angular momenta that was being canceled out by neighbors. And so they're so grounded and stable that then it takes a lot more energy to break them apart. The shell model was championed by two scientists, Maria Geppert-Mayer and Hans Janssen. And they actually won a Nobel Prize in 1963 for their work in the model. Maria Geppert-Mayer was, at the time, the second woman to win a Nobel Prize in physics. The first one was Marie Curie. So, in this model, each nucleon in a nucleus exists in their own shell, and they all have each shell, corresponds to some energy level. Energy levels are quantized, so energies are discrete. And the idea is that protons and neutrons kind of have their own neighborhoods they hang out with within the nucleus. They each have their own shell groups. According to the model, you have the protons and the neutrons occupying their own separate quantized states in their own little potential wells, and that makes up the nucleus. Any state in either proton or neutron neighborhood can actually be occupied by two neutrons or two protons as long as they have an opposite spin, so that their angular momentum has them spinning the opposite way. When you have a state filled by a pair of nuclei, by a pair of nucleons, that actually ends up canceling the overall angular momentum for the whole state, for the whole shell. So when every shell in the neighborhoods are filled evenly, all the momentum is being canceled out, therefore lowering the overall energy of the atom. Therefore, it's more grounded. Therefore, it's harder to break it apart. So that's why it has more binding energy. Also, in the proton neighborhood, protons, it is favorable for protons to share the same shell so that their angular momentum cancels out and lowers the overall energy. The effect of Coulomb repulsion still makes it so that paired protons are a bit less desirable than paired neutrons. So an atom is more stable with more neutrons and protons due to a lack of Coulomb repulsion. And so to minimize, to ground the nucleus as much as possible, the nucleus favors having more neutrons. And that's why for heavier elements, they tend to have more neutrons and protons because it's more naturally favorable. In other words, what the nucleus wants to do is it wants to bring all these particles in to form itself and shed as much energy as possible. The best way to do that is to basically bring as many neutrons together and protons together, but preferably neutrons, and have them all paired up together so as to have their spins be canceling out. And therefore, it creates a tougher nucleus that takes more energy to break apart. Modern ideas for what the nucleus is all about actually combine concepts from the liquid drop and the shell models, and lots of research is still being done today. Anyways, that's all we'll talk about for now. I hope you join me next time.